So we've come a long ways. We have this lovely equation here that relates a change in temperature over time in this control volume, partial derivative. With respect to this term here, which is a divergence of the flux, or the gradient of the Q, and then we have that last term for the generation from reactions or something else that might be taking place inside of this small control volume. We have a problem, though, still. The problem is that we have one equation with two unknowns. We have a partial differential equation that is, I got two dependent variables. One of them is temperature, and the other one is Q, which by itself is a function of position and time. So without some extra relationship, we're not able to take this problem any further. And what we're going to do is work on understanding how to understand what Q is and how Q relates to temperature. And we have help, as this was thought about quite some time ago by a scientist named Fourier, who was from 1768 to 1830. Fourier, I imagine he had curly hair, but I'm not sure, so this is Fourier, and he was a researcher, so he had a bow tie. Okay. And he studied the qualitative, not quantitative, qualitative, and quantitative heat flow. How does heat go from one region to another? And Fourier made the following observations. One is, if the temperature is constant in a region, then there is no heat energy flow. There is no heat energy flow. Okay. Two, if there are differences in temperature, in T, heat goes from hot to cold. It flows downhill. Number three, the greater the difference in temperature, the greater the T difference. I'll just put a little caveat. For the same material, the greater, the energy flow. Basically, if you have a big difference between hot and cold, the energy is going to flow much faster in that situation. There's also a much, much bigger gradient. Number four, different materials have different properties for heat flow, lead to different energy flow. Okay, so what he did was he did some experiments and then came up with an empirical relationship, which is Q is equal to minus K times dt dx. He did these at steady state, so it's total derivatives, and we have here K. This is called the thermal conductivity. 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 And this is the empirical relationship that we can then use to relate temperature, which is what our other variable is, our other dependent variable is, and x, which is an independent variable, to the unknown that we had in our equation q. But question, why minus q? Well, heat, according to Fourier's law, transfers down from hot to cold. So if the temperature profile from T, from this temperature in that region of space to this one is like this, the slope here is the temperature dx, change in temperature as a function of x. And so is this slope less than, greater than, or equal to 0? Well, the slope here is negative. It's less than 0. So imagine yourself being on this. Let's say you're on a sled or toboggan, and you're heat. You're going downhill. So dt dx is, the slope is less than 0. So for q, no, not g, q, to flow downhill, it has to be equal to minus some k times dt dx, because the minus times a minus is a positive. And that's how we define heat flux going down the hill. That is the end of this small snippet of the introduction of Fourier's